Okay, so let us get into a discussion of what this term state function means. So here's a definition of state function, or I should say the state of a system. It's basically the exact condition of that system at a particular point in time or at a fixed instant. So basically, this refers to things like whether or not it is in a solid, liquid, or gaseous phase, whether or not its temperature is at a certain value, etc., right? So it can encompass a wide variety of properties. Now, the state is determined by the kinds and amounts of matter present, the structure of this matter at the molecular level, and the prevailing pressure and temperature. So these are all the things that will affect the state of a system. And then we get to the state function, the definition of which is given here. It is basically a quantitative property that has a unique value that depends only on the current state of the system and does not depend on how the state has been reached. In other words, it's not dependent on the history of the system. All right. Let me just say some more things about this whole concept of state, because I'm quite sure you're familiar with that term when used in the context of the different phases of matter. You have the liquid state, the gaseous state, and the solid state, right? But as you can see from this definition here, excuse me, the term state is more complex than just that. So for example, let me go back to this PowerPoint. Let me insert a new page. And just to give you a brief illustration, just so that you understand what we mean by the state of a system. So if I were to have, let's say, choose a pen here. So if I were to say I have hydrogen at 1 atmosphere pressure, and a different sample of hydrogen at 2 atmospheres pressure, and these are both gases, right? So these are both gases. They are based on the fact that the pressures are different. That means that these hydrogen samples are in different states, even though they're both in the gaseous phase, but in terms of the definition that we just talked about, they're in different states, all right? Let me give you another example. Let's say I had copper at, let's say, which is a solid, at, let's say, 50 degrees Celsius. And let's say I heat that copper to 70 degrees Celsius. All right? Again, these are two different states, just by the simple fact that the temperatures are different. All right? They're in different states because basically at the particle level, at the atomic level, the atoms of copper in under these two different temperature conditions will have different energies, right? And because they have different energies, they're in different states. So I'm just mentioning that so that you understand what the term state in this particular context. Okay, so let me get back to the PowerPoint slide here. And let me get now to a discussion of a very important law. The first law of thermodynamics, which is the same thing as the law of conservation of energy. And basically what this law says is that in any chemical or physical process or change, energy will be exchanged between the system and the surroundings, but no energy can be created or destroyed. All right, so that's basically what this law says. So whatever the amount, another way of stating it, and I've seen this in some textbooks, basically it says that in physical and chemical changes, the total energy is conserved. That's another way of stating that law. So based on that law, we can come to certain conclusions, right? So the fundamental assumption of this law is that energy cannot be created or destroyed. And the inference that we can come to based on that statement is that the internal energy of a system is simply the difference between the energy between its final and initial state. So that's a conclusion we can come to based on the first law of thermodynamics. So mathematically, we can express that idea using this equation. The change in internal energy, delta U, and by the way, in some textbooks and other literature, they would use E instead of U for internal energy. All right, so just to let you know. So we're using U for our purposes here. Delta U is equal to U final minus U initial, the final internal energy minus the initial internal energy. Now, another conclusion we can come to is that if the energy change occurs only as heat and or work, then delta U becomes equal to the heat change plus work. All right? So this here sometimes is also stated as the first law of thermodynamics. In actual fact, it's a conclusion that we arrive to based on the first law of thermodynamics. The change in internal energy is equal to the heat change plus the work that is done on the system. All right? Now, another important thing that we need to know about this equation is the importance of the signs that we use for Q and W and what they mean. So we're going to look at the sign convention, and this is very important for a lot of things that we're going to do after this. So if energy is entering a system, right, it carries a positive sign. The change in energy is carries a positive sign, which means that heat is absorbed by the system and or work is done on the system. So basically, if the energy change, delta U, is positive, that means that that is so because one or both of these two things are happening. The heat is absorbed by the system and work is done on the system, or the work is done on the system. On the other hand, if you have energy leaving a system, that means one of two things, or one or both of two things. Either the heat is given off by the system and work is done by the system. All right, so it's very important that you understand and correctly interpret what the sign of the different terms mean. In this case, we're talking about energy, but you're going to see it also apply to heat and work. In fact, let's look at this particular example right here. And this important example underscores why it is very critical that you use the appropriate signs when it comes to certain problem-solving exercises. Okay, so this question says a gas does 135 joules of work while expanding, and at the same time it absorbs 156 joules of heat. What is the change in internal energy? So the first thing I'm going to write down here is a formula. Delta U is equal to Q plus W. That's a formula, all right? That's a formula we'll be working with. So the question now becomes, what is Q and what is W? But not only that, we have to make sure that Q and W that we're going to use in this equation have the correct signs. So let's deal with Q first. Q, of course, represents the heat change. And according to the question, the gas absorbs, very important, I'm underlining right here, absorbs 156 joules of heat. So what that tells us according to the sign convention is that Q is positive. So delta U here will be equal to Q, which is positive 156 joules. All right? Then it says here, well, to begin with, the gas does 135 joules of work. So does, what does mean? Basically, that means that the gas is doing work against the surroundings, which means that according to the sign convention, work is negative. So we're going to add the value for W, which in this case will be minus 135 joules. And therefore, Q, or I should say U, or delta U, will be equal to 156 minus 135, which is equal to 21 joules. So the answer here will be 21 joules. So it's admittedly a relatively simple example, but it's important that you use the correct signs, all right? And therefore, you have to make sure that you interpret the question carefully so that you use the appropriate signs for the different values of Q and W. Okay, continuing. So let's move on now to a discussion of heats of reaction. So, and this is where thermochemistry actually kicks in as a topic here, because now we'll be looking at the relationship between chemical reactions and the energy changes usually in the form of heat changes. So let's define what we mean by the heat of reaction. It is the amount of heat exchanged between a reaction system and surrounding, and that's it. So in this context, we have two other definitions, two other terms that you need to be aware of. One is, let me change back the pen here to, okay. So at this juncture, we need to distinguish between these two terms, exothermic and endothermic reactions. Okay, so let's talk about what we mean by the term exothermic reaction. An exothermic reaction is basically a reaction that produces heat, all right? And if this reaction is taking place in an isolated system, that means that the temperature will increase. So in actual practice, what this means, for example, let's say you have a reaction that is taking place in a test tube. For example, let me give an actual example. If you add potassium hydroxide to water in a test tube or a beaker and you stir it, then eventually it's going to feel hot, right? And what that means basically is that that process is an exothermic process when the potassium hydroxide dissolves in water, right? It's going to feel hot when you feel the outside of the test tube or the beaker. An example of an exothermic process, all right? Now, in that particular situation, the system goes from a higher to a lower energy, right? Because as it goes from the higher to the lower energy, it's losing heat